Okay, here we are, last example for hyperbolas, and then we're going to move on to our really awesome conic artwork. So I know I talked to you all today about who is liking the whole flipping the classroom thing and who is not. Hopefully this video is a little less strobe-ish. I've played around with some of the settings and I promise you I'm working on a solution to all of that right now. So let's get into this example. So here we go. We have y minus 2 squared over 9 minus x plus 1 squared over 16. So this is the type of hyperbola that is not centered at 0, 0, and so it gets a little bit more complex, but this is going to be our last example. So here we go. Very first thing that we want to do, again, just like we've done in all of the last problems, is we want to get this so that we have numbers squared on the bottom. So we can write this as y minus 2 squared over 3 squared minus x plus 1 squared over 4 squared equals 1. And now let's go ahead and graph it. So let's draw our graph over here. And here's something that you really want to make sure that you're paying attention to. So we know that the center of this is not at 0, 0 because there are things being added to and subtracted from x and y, but really make sure you're paying attention to what is where. A lot of us, I think, would look at this and go, okay, the center is at 2, 1. But remember, x and y can switch positions here. So the center is actually at negative 1, positive 2. The x is over here. Okay, so make sure you're paying attention to that. So let's put that on here first. Negative 1, 2. And then we're going to do the same thing that we were doing yesterday. So the 3 is directly under the y, so we're going to go 3 units up, because y is up and down, and 3 units down, and then 4 to the right and 4 to the left. And we're going to draw a dotted box through that. So make sure when you're doing these that you actually make the box and the diagonals or the asymptotes dotted, because they're not actually part of the graph. We use them to help construct the hyperbolas themselves to make them mathematically accurate, but they're not actually part of what the hyperbola is supposed to be. So that's why you're making them dotted. Now this is something that I've gotten feedback from you all in class, that we look at whichever number is bigger and that's which way the curve opens. That's not the case. You always want to do whichever one is positive. So this, it's like there's an invisible plus sign here in front of this y, so that means the curve is opening up in the y direction. Okay, whichever one is positive, that's which way the curve opens. It doesn't have anything to do with which number is bigger. Okay, so the way that we draw them again is we go along the box and then really close to the asymptotes but not touching. So what happens is, as the curve, let's see, I'm going to do this here. As the curve extends, it gets closer and closer to the asymptote. So some people have a tendency to draw these and make the curves go back inward. You don't want to do that, okay? So let's do this one, close to the asymptote but not touching, and so on. All right, so these are our vertices right here and right here. So let's write those down. So the vertices are at negative 1, 1, 2, 3, 4, 5. So negative 1, 5. And at negative 1, 1, negative 1, negative 1. There we go. So this is a vertex and a vertex. Okay, so the next piece, we need the foci. So again, the only place where the foci, that you get them is c squared equals a squared minus b squared is when you have an ellipse. Everywhere else, it's the traditional Pythagorean theorem that we're used to, or c squared equals a squared plus b squared. So it's something to remember. Okay, so c squared equals a squared plus b squared. So in this case, we go c squared equals 3 squared plus 4 squared, or 9 plus 16, and that equals 25. 25, I almost drew 29, 25. And the opposite of squaring is square root. So we go c equals positive or negative 5. Now, all of the problems where we had nothing being added to or subtracted from the x, or the center at 0, 0, we would just say that the foci are at 0 plus or minus 5. But the problem is the center is somewhere else here. So we have to take that into account. So the foci, this is saying this is plus or minus 5 units from the center. So we have to take that into account, okay? So let's bring the center down here. Okay, so -1, 2. I'm going to do this twice. -1, 2. And the reason I'm going to do it twice is because we have 0, +5 and 0, -5. Now, remember, the way that I knew that the C was going in for the y coordinate instead of the x is because our curve opened up in the y direction. The foci, they're going to be somewhere out here, okay? So make sure that you have that. So if it opened up in the x direction, it would have been 5, 0, and -5, 0. So all we're going to do is we're going to add these together. So -1 plus 0, that's -1. 2 plus 5 is 7. So there's one of them. And -1 plus 0 is -1. 2 minus 5 is -3. So these are the two coordinates of our foci. Okay, and actually, you can actually go back and put those in the graph and see if it makes sense. -1, -3, -1, -1, 2, 3. So one of them is right here, and the other one, I'm going to put an F there for foci. And then let me move this up just really briefly. -1, 7, that's the other one. So that makes sense. Okay, if you had them somewhere in here, doesn't make sense. So something's funky. Okay? All right, last piece, we've got the asymptotes. And again, these are a little bit more complex because we are not centered at 0, 0. So we're going to use a different form of our equation. Okay, so traditionally, in the past couple of problems, because we were centered at 0, 0, all we did was we used slope-intercept form, or y equals mx plus b, and plugged some stuff in. Not the case here. Okay, we're actually going to use point-slope form to come up with our equations for our asymptotes. Okay, so I'm going to use the center here for x1 and y1. Okay, so let's write this down here. The center is at -1, 2. We know it goes through -1, 2, our asymptotes. Let's just refresh our memories. Up here, that's one of the asymptotes, and that's the other one. We know that it goes straight through the center, so that's the point that we're going to use for x1 and y1. Let's actually write that on here so that we don't get confused. So x1 is this, and y1 is 2. Okay? Then we are also we need the slope. Let's actually do this. Put m equals, let's actually go back and see what the slope is. So it's rise over run. So we rose 1, 2, 3 spaces and ran 1, 2, 3, 4 spaces. So the slope is 3/4, but it also could be -3/4, because from here, to get this line, it's +3/4, but you also can go down 3 or -3 and right 4. So we're actually going to put that on here, that the slope is plus or minus 3/4. We're going to take these pieces of information and plug them into this equation to get our equation of our asymptotes. The thing that's nice about this is we're just going to leave it in point-slope form. Okay, so here we go. Y minus 2 equals plus or minus 3/4 times x minus -1, which again translates to x plus 1, so it's y minus 2 equals plus or minus 3/4 x plus 1. We're going to leave it like that. Okay? So, make sure that you have questions in your margins, and let me go ahead and put up the 2 extra credit problems, and so let's do this now. Let's put this up here. Whoop. Okay, I'm going to have to, there we go. That works. Okay, so for the extra credit, you have those two. One is centered at 0, 0, one is not, so you have to know both of them. And then the in-class work is listed here. You already will have done some of this in class already, so you can do whatever you have not done in class for homework on Monday, okay, or over the weekend, whatever you prefer to do. On Monday, we're going to start looking at conic section artwork, so I'm going to go ahead and do a really short video for that. It will either be ready today or next week, okay? So, everybody have a great weekend.